Without any further ado, Professor Dave Jewitt.
Okay. What I wanted to do in this talk is give an introduction to the solar system, which has changed quite a lot since I came here. I think it was about 20 years ago. I would like to do this talk in three parts. First part is a quick one, basically an introduction to astronomy in Hawaii. Then give you this overview of what we think we know about the solar system now that we didn't know even quite a short time ago. And then at the end, say a few words about the origin of the oceans. Astronomy in Hawaii, obviously, is based on the existence of this tall mountain, Mauna Kea, on the Big Island, 14,000 feet tall, with a bunch of telescopes on the top. And the reason we have an Institute for Astronomy, and why astronomy is a relatively big thing at the University of Hawaii, is this mountain is a fantastic place to do astronomy on the surface of the Earth. And you might say, well, but isn't space a lot better because, you know, space never has clouds, it's perfectly clear all the time. And the answer is space is a lot better, but it's very, very hard to do anything in space. And so it turns out the Earth is a really good place, A, to live, and B, to attach big telescopes to. And so we can have on the ground telescopes that are much, much bigger than any telescope that we're capable of launching into space. So in fact, the Hubble telescope, the most famous one, is 2 meters in diameter, about 6, 7 feet in diameter. It is comparable in size to the smallest telescope on Mauna Kea. So we have much larger telescopes on the mountaintop. And we can see very, very faint things and very fine details in the sky that we can't see from space. So here's a picture I took last year after a snowfall. There's more snow, as you probably know, on the mountain in the last couple days. So this is a fairly typical winter picture. Looking south towards Mauna Loa in the background right there. And this is one of the cones, Goodrich cone, this one is called, next to the telescope, next to the telescopes at the summit of the mountain. So here is a picture of 3 of the particularly nice telescopes. These are the world's largest, the Keck telescopes. This is a Japanese Subaru telescope. These are 10 meters in diameter. This is 8 meters in diameter. In the background is Maui sticking up above the ocean there. So if you haven't been to Mauna Kea and you have a chance to go there, you got to go because it's kind of a fantastic place. Even if you don't like astronomy, it's a fantastic place to go. Okay, so what's really good about it for astronomy is that it is above a significant fraction of the atmosphere. The atmospheric pressure at the top of the mountain is about 1/3 less than it is in this room because we're simply so high. It's very, very dry, and it's very dry in part because we are above what's called the inversion layer. So here's a picture of sunrise. Here's the sun coming up. And as soon as the sun comes up, you can see that below the summit is this boiling cauldron of cloud that is swirling up, convecting up from the ocean, but it's capped. It tries to rise up and reach the top of the mountain, but it utterly fails. It's capped by this inversion layer that prevents the convective cells from rising up high. And then as sunset approaches, this thing calms back down again. The sky above the mountain stays clear. Here comes the shadow of the mountain going out across the sky, the shadow of the Earth going up, and then it's nighttime. And then stars begin to cross the sky. So that's and here comes the moonrise later that night. So that's the essence of Mauna Kea. We're at a very high altitude site where the atmosphere is very dry, where the wind flow, the flow of the air over the mountain is very smooth, where turbulence is very small, and all of that means that the seeing, the resolution that we can achieve in the sky is very, very high. So those are special features of Mauna Kea. Now, people know that everywhere. And sometimes people who work for TV companies and other things, movie companies, call up and say, we'd really like to come out to Hawaii and take a movie of astronomers observing. And we'd like to take a movie of you observing. And I always say, well, you know, it's probably not the way you think. It's probably a lot more boring than you think because we sit at a computer and we type on the keyboard and we don't really look through the telescopes anymore because we have detectors that are much, much more powerful than our eyes, so there's no point in using our eyes. It's much better to use the electronic detectors. So maybe you shouldn't come out. And they always say, yeah, we understand that, but we really want to come out. And then they come out and take videos. And so to show you the kind of videos that they can get, I took this movie a few months ago while I was observing at the Keck telescope. And it's taken at high speed to accentuate the action. So we're sitting in a room, actually, controlling the Keck telescope. This is Pedro Lacerda, who was my postdoc from Portugal. He's gone off to Ireland now. We're looking into a computer at data that comes down from the mountain, and we're studying the data from the world's biggest telescope, trying to figure things out. So this goes on and on and on. We never stop. After a while, you see that we get a little bit hungry, and we start to go out and get food and come back and eat things. There we go. We disappeared again for more food. We're coming back to check the data. This goes on all night. There's the apple. Pedro takes a mysterious dive on the floor, which I don't quite understand. It gets cold, so we go out and we get our jackets on. And it just goes on hour after hour after hour after hour. So it is definitely I don't know why you're clapping. It's definitely not the kind of thing you want to see on TV, but that's what people come out to take movies of for some reason. What they really want is a movie of the telescopes and things on the summit. But that's astronomy happening. That's what it looks like when we do what we do. So it doesn't look good, actually. It looks pretty ugly. But the purpose is good. So the purpose is to use data to understand the physical world. And the thing I like to say when I show this movie, and I'm going to say it now, is that this is what distinguishes us from people interested in politics or people interested in religion, because people interested in those things essentially just make things up as they go along. They don't have an absolute point of reference. The good thing about science, and the special thing that's an idea that's like 500 years old now, and not much older, is that we have to have a very firm anchor point in the physical world. So we have to base what we think upon what we observe. Okay, so the primacy of observations really controls the whole thing. It's what science is. And that's why we do this ridiculous dance at the telescope on chairs with wheels and looking into computers and putting on coats and eating sandwiches and so on all night long. It's because we have to. This is the basis of what we do. Okay, so that was my mini intro to astronomy on Mauna Kea and astronomy in Hawaii. Let's have an overview of the solar system as we now see it to be. So in the past, when I was a kid, the solar system was basically the planets. We'd say, oh yeah, the solar system, that's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and there's a couple more beyond that. And then not much else. So what's happened in the last 15 to 20 years, mostly through observations taken on Mauna Kea, is that we have uncovered a completely new view of the solar system, in which the importance of the planets is not diminished, but a whole new set of bodies has emerged as being super important in terms of giving us information about how the solar system formed and the ways in which it's evolved since it formed 4.5 billion years ago. So what we now see is that we can divide the solar system usefully into these different bits or different domains, which I'm calling the domain of the terrestrial planets. The terrestrial planets are Mercury, Venus, Earth, and Mars. And in this domain, I probably should include the asteroids as well. The asteroids are very, very small compared to the other terrestrial planets. These are rocky things. They're like the Earth. They're made primarily of rock and metal. Like the Earth has a core of iron with some nickel mixed in, and the rest of it basically is silicate rock. Same is true for the other terrestrial planets. These bodies, we think we have a pretty good handle on. We may be wrong, of course, but we think that we understand how they're built. We think we understand in some level of detail how they grew. And they grew basically by collisions between little tiny dust particles in this swirling nebula surrounding the sun in the beginning. The dust particles collided and stuck to make bigger dust particles, and then these dust particles grew into things the size of grains of sand, and then into grape-sized things, pebbles, and then boulders, and then things as big as the state of Hawaii, and then up and up and up, eventually culminating in the four large terrestrial planets that we see. The biggest one is the Earth. So that is understood in part because we know a lot about the terrestrial planets. And we know a lot about the terrestrial planets, not least because we live on one. So we can study the rocks under our feet, and we can drill into the Earth, and we can send sound waves through the Earth, seismic waves, to probe the deep interior structure. We can do all these measurements that we can't do on other kinds of body in the solar system, and we know a lot about terrestrial planets. Also, we've sent spacecraft to the other terrestrial planets. There's one at Mercury now. We've been to Venus. The Russians have landed on the surface of Venus. We've been, obviously, to the Earth. We're still visiting the Earth every day. We've been to Mars a lot. We've visited asteroids. We know a lot about these bodies because they're nearby and they're relatively easy to study. So that's the domain of the terrestrial planets. Beyond the terrestrial planets, the character of the bodies changes completely, and we have objects that we call the giant planets. Giant, obviously, because they're much bigger than the Earth and the terrestrial planets. And so they are Jupiter and Saturn and Uranus and Neptune. And just for reference, Jupiter is about 11 times the diameter of the Earth. It's about 300 times the mass of the Earth. Its composition is completely different from the Earth. It's called a gas giant because it's made mostly of hydrogen and helium, which are the same two elements that dominate the composition of the sun. So the gas giant planets, Jupiter and Saturn, are similar in many ways to the sun, except that they don't support nuclear fusion, and so they're not hot. They don't radiate much energy because they don't have the conditions in the inside that are fierce enough for fusion to occur. What do we know about the giant planets? Well, we know their basic characteristics. We know how big they are, how massive they are. We know pretty much what they're made of. We don't really know how they formed. So we have different ideas about that. And the reason that we're not really sure what's going on with the giant planets is basically that we don't have as much data about them as we have about the terrestrial planets. So we see features on the surfaces, on the cloud surfaces of these planets. They have no solid surface, no physically hard surface that you can land on. We just see the cloud tops, and we make inferences about them from observations primarily of the cloud tops, and that's a very difficult business. There are two ideas for the formation of the giant planets. I'll talk about those just in a moment. Let me just speed ahead to the third domain, which is the domain of the comets. So we've known about comets for a long time. We know that comets are individually small, but it turns out there's a huge number of them. And it's that huge number of comets, and it's the distribution of comets and the distribution of the orbits of comets as they whiz around the sun that can tell us, it turns out, quite a lot about the origin of the solar system. So the movie in the background shows what you would see if you were on a spacecraft leaving the sun and moving out radially, just to give you an idea of the scale of the solar system. There goes Jupiter. There goes Saturn, 10 AUs from the sun. The Earth is 1 AU from the sun, of course. There goes Uranus, is 20 AUs from the sun. Here comes Neptune, it's 30 AUs from the sun. Coming up soon is Pluto, which has a big satellite called Charon, so we'll see this double thing nip by. There you go, that's Pluto. It's 39 AUs from the sun. And then we end up with another big Kuiper Belt object that's even further away from the sun. And then because that movie was quick, I made it repeat. So here's the sun, and then we see Mercury, Venus, Earth at 1 AU from the sun. There's the moon going by 2. Yeah. Mars, Jupiter, the biggest one. Saturn with the famous rings, 100 times the mass of the Earth. Uranus, about 16 times the mass of the Earth. Neptune coming up at 30 AU, also about 16 times the mass of the Earth. Then Pluto, a pathetic little thing. And then another one coming up after it. So the movie's good because it just shows you that most of the solar system is empty space, something you know, but it's just hard to visualize how empty it is. It's fantastically empty. It's just an incredible vacuum, the likes of which we cannot generate in our labs, even now. So here are pictures of the terrestrial planets, Mercury, Venus, Earth, and Mars, at the correct relative scales. So you can see the Venus and the Earth are basically the same size and the same mass. Mercury is small, and Mars is about half the size of the Earth. And as I said, we think we know quite a lot about these planets because we live on one of them and we've studied them in great detail. The most interesting one and the most spectacular one, of course, is the Earth, in part because it's got a fantastic atmosphere, but mostly because it's geologically very active. And so you know that we have these plates on which the continents float. Here's Africa, here's the Middle East up here, Europe's over here, the US is around the backside, here's the South Pole, here's Antarctica. And they all move around because the interior of the planet is basically mobile, it's convecting, and it carries the plates around and they bang into each other, and when they collide they make mountains, or one plate gets pushed under the other, and we have a subduction zone. A lot of stuff going on the Earth compared to the other terrestrial planets. The giant planets, also shown to the correct relative scale, are Jupiter, the biggie, Saturn, so this is 300 times the mass of the Earth, 100 times the mass of the Earth, 16 and 16. And here's roughly the size of the Earth shown by this dot here. So these things are really, really big. These are enormous planets surrounding the sun. And then as we go out, we come to the comets, which are the main subject of this talk. Let me just backtrack and tell you the thing I forgot to tell you, which is how we think these giant planets form. Whereas the terrestrial planets form when little dust grains collide and stick and grow bigger to make pebbles and boulders and so on, we know that can't happen for the giant planets because they're not made of rocks. They're made mostly of gas. And so the question is, how do you make a big ball of gas in the solar system surrounding the sun? And there are two ideas. And they may both be wrong. Probably one of them is correct. One idea is that when the solar system was forming, the sun was surrounded by this extended disk, mostly of gas, consisting of hydrogen and helium, that fell in towards the sun from the interstellar medium. And if that disk were sufficiently massive, it might have had enough gravity to cause the disk to be just unstable by itself. So it might suddenly have reached a critical size and a critical density and then collapsed in on itself because of its own gravity. So that's called the disk instability model, in which the giant planets basically pop into existence almost by magic. Okay, maybe that happened. Many people think it's more likely that the giant planets formed by a process called nucleated instability, which is pretty much the way a raindrop grows inside a cloud above the surface of the Earth. So maybe you know that the water molecules in the air don't easily stick to each other to make drops of water. They go the other way around. They tend to evaporate. So the way a raindrop forms is that there's some particle called a condensation nucleus. Usually it's a piece of dust or a piece of salt from ocean spray, something like that. And that little condensation nucleus acts as an attractor for water molecules floating around in the atmosphere. And the water molecules can then stick onto that condensation nucleus and then grow to make a bigger drop. So every drop, in principle, has a little tiny microscopic seed in the center that caused the thing to grow. So the counterpart for the planets, the giant planets, is that we believe that these bodies started like terrestrial planets. So they started as rocky planets, just like the Earth, but maybe 5 times more massive or 10 times more massive. And then when they grew to a particular critical size, those growing terrestrial planets, out where we now see the giant planets, suddenly had enough gravity to begin to pull in the gas from the surrounding nebula, from this disk of gas swirling around the sun. So they grow in mass until they reach a critical level, which people think is about 5 or 10 Earth masses. And then suddenly they can pull in the gas in what's called a hydrodynamic flow. It's like a river of gas coming into the body. And then the mass shoots up because there's a huge amount of gas swirling around the sun that can be picked up by these condensation nuclei. So that idea suggests that each of the giant planets should have in its center essentially a terrestrial planet, some rocky or icy body that acted as a condensation nucleus for the growth of that planet. And you might say, well, that's a nice idea, but you'll never know whether that's true or not. But in fact, from studying the motions of satellites as they go around the planets, spacecraft, and also natural moons of the planets, we can actually figure out how does the density vary deep inside the planet. And there is now pretty good evidence for the existence of such a dense core in Jupiter. There is, I think, undeniable evidence for such a core in Saturn. And Uranus and Neptune, which are a little different in various ways from Jupiter and Saturn, are mostly core. So they're 16 or 17 Earth masses of stuff, and maybe 5 or 10 of those Earth masses of material are the original cores. So they just don't have so much hydrogen and helium added on top. So anyway, those are the two models. I'm not going to try to defend one or the other in particular. I personally like the second one, the nucleated instability model. But the fact that there are two models, and they're quite different, one is the spontaneous collapse, one is the nucleated instability, tells you that we don't know in detail what's going on. We have lots of possibilities there. By the time we get to the comets, this vagueness increases, by orders of magnitude. So we know much less about the comets than we know about the giant planets, and we know much less about the giant planets than we know about the terrestrial planets. So we have these three domains. The first one is kind of interesting. We have very deep and sophisticated knowledge from spacecraft and from other observations. The second domain is kind of mysterious, but very interesting. And the comets are almost unstudied. I mean, we're still discovering major new populations of bodies containing comets, large numbers of comets. So the first one to be discovered was this one called the Oort cloud, which was found by a little Dutch man about this tall. It's okay to be that tall, no problem, in 1950. And he inferred the existence of this spherical swarm. Here's the sun, this spherical swarm of comets surrounding the sun, about 100,000 AUs across. Now remember, the distance to Neptune is about 30 AUs. So this is much, much, much bigger than the size of the planetary region of the solar system. The orbit of Neptune actually would be completely invisible on this plot. It's so small, we couldn't see it. So this swarm of comets is inferred from the long period comets, which seem to fall into the solar system randomly from all directions. The equal numbers coming in from the northern hemisphere, from the southern hemisphere, in the direction of the Earth's motion and behind the Earth's motion and so on. It's a spherical infalling population of comets. And these things, we think, have been there since pretty much the origin of the solar system. There are probably almost 1 trillion comets in the Oort cloud. There's a lot of comets. Comets individually are small, maybe a few miles across, but there's so many of them, when you add them all together, they carry quite a lot of mass, and so they're important. And their distribution is important for understanding the solar system. And then down at the bottom right is this thing that we call Kuiper Belt, which is much smaller. So here are the orbits of the planets, Jupiter, Saturn, Uranus, and here's Neptune going around like this. And the Kuiper Belt is like this bicycle tire surrounding the solar system that starts at the orbit of Neptune and goes out. So it's kind of a disk. It's kind of fat, so it's kind of a donut, maybe more than a thin disk. And I'll talk a little bit more about that in just a moment. But this turns out to be the source region for what we call short period comets. So comets that don't fall in from the Oort cloud instead fall in from this region called the Kuiper Belt. Okay, so this is 1950, this is 1992. This we discovered at the telescope on Mauna Kea. Oh, here's a summary of those two things. So Oort cloud, 1950. The comets in the Oort cloud probably formed between the giant planets and then were ejected by the giant planets. They were scattered by the gravity of the giant planets outwards to large distances, and they inhabit this big swarm surrounding the sun. The temperature out there at the present time is about 10 Kelvin. It's basically close to absolute zero. I don't know what that is in centigrade, Celsius. It's probably minus 260 or something like that. It's really cold. So they're absolutely frozen. And we think of them as snowballs frozen from the beginning of solar system time. But they formed at temperatures that were a little bit higher, maybe up to like minus 150 centigrade, something like that, in between the orbits of Jupiter and Neptune, and then were kicked out. So they actually formed closer to the Sun than the Kuiper Belt, which is beyond the orbit of Neptune, but then were displaced outwards. Kuiper Belt objects now are about 50 Kelvin, so they're hotter than the Oort cloud comets in their storage locations, but they formed colder than the Oort cloud comets. And then very recently, and I'll come to this at the end of the talk, Henry Shea, graduate student at the IfA, and I discovered this third population, which we call the main belt comets, which are comets that actually live in with the asteroids in between Mars and Jupiter. And they've been faking us out, for decades or hundreds of years now, because they have this dual character that we only just recognize. They are comets, but they're also asteroids. I'll talk more about those soon. So we now know of these three reservoirs for the comets. We know three places where the comets can come from, and there may be more, okay? There might be a lot more, as far as we know. The point is that it's still the case that we're discovering the solar system. So people often think, yeah, the solar system's next door. We must know everything. We've sent spacecraft here and there and everywhere. We've got to know everything there is to know. It turns out that that's quite the reverse of the truth, that most of the solar system, I think, remains to be discovered, and we're still discovering it with telescopes on Mauna Kea. So I don't want to horrify you with this diagram, but the point is to show you that we identify the asteroid belt and the Kuiper Belt and the Oort cloud as three distinct reservoirs, and then they produce all these other different objects. So these are the Trojans, which are bodies that co-move with some planets. The Centaurs are things that just escaped from Kuiper Belt. In the future, the Centaurs will become Jupiter family comets. The Halley family comets maybe come from the Oort cloud. The long period comets do come from the Oort cloud. There's a whole bunch of different things on this diagram, too complicated to talk about here, but they're all connected. So what's happened in the last decade or two is that people no longer study things in these boxes individually, because it doesn't make any sense. People study the way in which bodies in this box might be related to bodies in this box, and this box, and this box, and so on. So we have this growing feeling that the small bodies in the solar system are this historically connected population, not just weird, freakish things that exist in one box or another box to be studied in isolation. So it's kind of a qualitative change in the way people think about the solar system. 20 years ago, you could go to some astronomy department and find somebody who was an expert on those. Oh yeah, I'm an expert on LPCs. Well, big deal. Now we don't care about that. We care about the way in which LPCs, the long period comets, relate to the Oort cloud and relate to the Halley family comets, and maybe relate to other things in this diagram. So it's the connections that are really important. Let's talk about Kuiper Belt. Here is a little movie that shows how we find Kuiper Belt objects and other things that move in the planetary system. So this is a galaxy, stars and galaxies. Here, this is an object which appears to move relative to the background objects. And so we're looking at a series of pictures, 1, 2, 3, 4, that are separated by about 15 minutes of time. And in 15 minutes, this thing moves a small part of its orbit around the sun. And so we distinguish this body from others as being interesting, A, because it moves, whereas the galaxies and so on are so far away they stay fixed, but B, because it moves slowly. If this were an asteroid near Mars or Jupiter, it would nip across the picture 5, 6, 7, 10 times faster. And we would say, oh yeah, it's another asteroid. But because it's going slowly, we're interested and we say, aha, that's a Kuiper Belt object. So that basic technique has been the key to understanding the solar system and to finding the Kuiper Belt objects. So the first one was in 1992. Since then, more than 1,000 have been discovered. I think the count is now 1,300 or something like that. It's a huge number of bodies. But they're just the tip of the iceberg. So we think that if we could survey the whole sky in the way that we've surveyed small parts of the sky, we would see 70,000 Kuiper Belt objects. These are basically supercomets, big comets, things about the size of the Big Island beyond the orbit of Neptune, 70,000 of them. And if we could see fainter objects and go down towards the size of the cometary nucleus, a few miles across, we'd probably see 100 million or maybe 1 billion objects in the Kuiper Belt. So it's a ring with a lot of stuff in it. There are 1,000 times more Kuiper Belt objects than there are asteroids. Asteroids are very famous. We've known about them for a couple hundred years, but it turns out the asteroid population is puny compared to the Kuiper Belt population. And the reason that we didn't know about Kuiper Belt is simply it's very far away from the sun. We can only see these objects in reflected sunlight. This is visible just because sunlight goes all the way out, reflects off this thing like a little mirror, and then comes back. And it's not even a good mirror. The reflectivity is probably 5 or 10%. It's probably not a very bright surface. So it's like looking at an interplanetary blackboard on the edge of the solar system. And it takes big telescopes, like the ones we have on Mauna Kea, and good electronic detectors to see these things. So this kind of diagram I will show and talk about. Don't get scared. It's not too bad. This is basically the distance from the sun. So 20 means 20 times the Earth's distance from the sun. This is 20 AU, 40 AU, 60 AU, 80 AU, and 100 times the distance between the Earth and the sun. This is the eccentricity represented by a number. So 0 means the orbit is circular. 0.8, so circular like that. 0.8 means the orbit is eccentric like that, like an egg, a long egg. So N shows where Neptune is. Neptune sits here, 30 AUs from the sun, in between 20 and 40, and its orbit is very closely circular. So Neptune is right there. These dots show the Kuiper Belt objects that have been discovered in the last, how many years? 16 years, since 1992. And what you see is that the distribution of Kuiper Belt objects is not random. They're not just splashed all over the diagram. They're concentrated in different groups. I'll just mention their existence and then we have to move on. The red guys we call the classical Kuiper Belt objects. They define a ring with a relatively sharp inner edge just beyond 40 AU and a relatively sharp outer edge at about 50 AU, 47 AU perhaps there. So these classical Kuiper Belt objects, there are many of them. Their orbits are nearly circular. The eccentricities are all small, so the orbit shapes are something like that. And these bodies, we think, can survive essentially forever against interactions with Neptune, simply because Neptune is over here and they're over there. Yeah, that's a big distance. Here's 30 AU, here's 40-something AU, so that's a large distance. And even though Neptune's a big planet, it doesn't really have any effect on these things. So we think these are primordial. The blue things are called resonant Kuiper Belt objects, and they're special. I'll just talk about these ones right here, 39 AUs from the sun. Now, one of these is extremely famous, okay? And it's famous because it's this thing called Pluto, which we used to think, at least in many cases, used to think was a planet of some sort. It's a matter of definition. You can still think that if you want to. Here's Pluto. Sorry, here's Pluto right there, this one. But you would never guess which one is Pluto if I didn't tell you, I suspect. And so one of the results of studying Kuiper Belt is that we realized Pluto's not special anymore. In the past, Pluto used to be this very, very freaky planet with this relatively high eccentricity and a large inclination. Its plane is kicked up relative to the plane of the planets. And it was very puny, very tiny compared to the other planets in the solar system. People used to say, yeah, Pluto's a planet, but it's kind of a runt. It's kind of a freak planet. But what we see is it's absolutely typical of the Kuiper Belt objects. Yeah? So it's changed its status. We now see it as, in fact, one of the bigger known Kuiper Belt objects. It just happens to have been discovered in 1930 and then mislabeled, misclassified as a planet by the people who found it, and kept that way until 1992 when we realized, aha, game's up, we know who you are. So these things, including Pluto, are closer to Neptune, and you might think that they would be kicked around by Neptune, but they're not. And the reason is that at this position, they complete 2 orbits around the sun in exactly the same time as Neptune takes to complete 3 orbits around the sun. So Neptune does 3, and these guys do 2 orbits. It's called a 3-to-2 mean motion resonance. And what that does is give these orbits some long-term stability. The interaction between Neptune and the Kuiper Belt objects is periodic, a bit like pushing a kid on a swing. If you push in phase with the swing, you can build up a large amplitude. If you just approach your daughter from behind and give random shoves at random moments, then she'll probably just fall off the swing. So these guys are stabilized by the same kind of effect, called a resonant effect. And there are other resonances. Here's another one here called 2-to-1, and there are other guys too. Then we see this big band of bodies. These are called scattered Kuiper Belt objects. We think these are, in fact, being launched outwards by interactions with Neptune. So we think they're not stable on billion-year timescales. They're slowly being pushed out in this direction. So they're being pushed out, in fact, towards the Oort cloud and the interstellar medium. And then these yellow things here are extremely unstable. They only live for 10 million years, and then they're gone because they hit a planet, or they come close to a planet, and the planet will sling them out, or they'll go in and they'll hit the sun after being comets for a little while. I'll skip over that one. So here's what it looks like. Kuiper Belt, these white circles are the orbits of planets, Jupiter, Saturn, Uranus, Neptune, and then these red things are the classical Kuiper Belt objects, and the other colors correspond to the previous diagram. The point is there's a big donut of stuff surrounding the planetary system that we did not think was there. So we've learned a lot from the existence of this previously unknown population. We have learned, for example, that there are many populated resonances, things like Pluto, but many more than Pluto. There are hundreds of objects trapped in Pluto-like orbits. And the only way that we can think of to trap these bodies is by a process called planet migration, meaning that the size of the orbit of a planet has changed with time. So specifically, we think from looking at the Kuiper Belt that Neptune must originally have been near 20 AUs from the Sun and scooted outwards to its present location at 30 AUs from the Sun. And that's planet migration. And why would the planets do that? We think they did that because in the beginning, the planets were ejecting lots of material from the planetary system out towards the stars. And when they eject objects, they throw out mass, they throw out energy, and they throw out what's called angular momentum, and that causes the sizes of their orbits to change. So we've inferred this planetary migration from just looking at the Kuiper Belt. We see that Kuiper Belt objects are in this fat disk. It means it's been stirred up by something. And we see that the total mass of material in the Kuiper Belt is quite small. At the present time, it's like 1/10 of an Earth mass. And the really interesting thing is that if you try to form objects in the Kuiper Belt, if you take this small amount of material and spread it over the Kuiper Belt, the timescale to grow a Kuiper Belt object is longer than the age of the solar system. So the objects that we observe cannot have grown in the observed environment. We think that probably the Kuiper Belt in the beginning was 100 or 1,000 times more massive than it is now. So what we're seeing is kind of a remnant or a shadow of the initial Kuiper Belt. So that's kind of interesting. If you put these things together, if you put together migration, which comes from the populated resonances, and you put together the idea that interactions between bodies can have been very important in the past, you come up with this thing called the Nice model. You come up with other models too, of course. There are many models, but this is a very pretty one. So in the Nice model, the planet orbits are migrating in early times. The sizes of the orbits are changing, and that means that the gravitational interactions between the planets become sometimes strong and sometimes weak. When the planets get into a mean motion resonance, in particular, when the massive planets, Jupiter and Saturn, get into a mean motion resonance, then the interactions are very strong. And what you see from this model is that those planets, when they're in a resonance, can literally shake up the entire solar system. So in this Nice model, which comes from these European people who live in or near Nice and published this model in 2005, shows the same solar system. This is distance from the Sun, 10. Here is where we now see Saturn. Here is where we now see Uranus. Here is where we now see Neptune. And this again is eccentricity, circular orbits and elliptical orbits. And they've simply calculated the motions of bodies as a function of time. So these are the planets, and the first thing, and this is the Kuiper Belt out here. And the first thing to happen is that the outermost planet kicks up this arc that looks surprisingly like the scattered Kuiper Belt objects. So these bodies are being excited by Neptune, and they're slowly drifting up in this direction out towards the upper right. The planets are jumping around because they're individually scattering planets, planetesimals, Kuiper Belt objects, comets, and every time one comes near, they exchange a little bit of energy and a little bit of angular momentum, and they move around. So they're bouncing around because they're scattering unplotted objects. Now, everything goes along smoothly, you think, for a long time. Here's the time in hundreds of millions of years. But in fact, this system evolves towards a catastrophe fairly soon. You can see a resonant population building up here in the model. This thing has the same basic flavor. Here are the classicals, here are the scattered, but suddenly it goes unstable, and the Kuiper Belt effectively explodes. So in this model, it's the migration of the planets towards a resonance shown by this red line. So when the planets go into 2-to-1 mean motion resonance, then the interactions between the planets become so strong that they literally shake the entire solar system. And when you shake the solar system, all sorts of weird stuff can happen. So here's the same model with a higher time resolution. This one has 1/10 of a million years per second. So here's the same model. The planets are bouncing around. Look what happens to the planets. Watch this one, watch this one. There you go, bang. So in fact, this planet is thrown out. This planet is what we would now call Neptune. This planet is thrown out into the Kuiper Belt, and it's such a massive body that it stirs up the Kuiper Belt like sticking your hand into a nest of bees. They suddenly get very excited and start flying around. So in this model, which may or may not be correct, of course, we don't know, the Kuiper Belt loses a lot of mass at this time. And this is a long time after the formation of the solar system, almost 1 billion years after the solar system accreted. So it grew 4.6 billion years ago. This thing, the modelers suppose, happened maybe 3.8 billion years ago. And they picked 3.8. In fact, they can get any time they want, pretty much, by tuning parameters of the model. They picked 3.8 because they're trying to explain the crater record on the surface of the moon, which some people think indicates a sudden burst of cratering on the moon at about 3.8, called the terminal bombardment, or the late heavy bombardment, that was basically found 30 years ago from mostly Apollo measurements. So maybe this happened. But the reason that we have this kind of model, and it's certainly a pretty model, I think you agree, is that we have this new view of the solar system based on observations of the small bodies in the solar system. So I just thought I'd show you a few pictures of individual small things. These are the nuclei of comets. On the left is a comet called, I call it Wild 2, but it's Swiss, I think it's called Wild 2. Wild 2, visited by a spacecraft with lots of depressions, many of which are not impact craters, although they may look that way. Here's the nucleus of comet Kahle in 1986, and here's the size bar at the bottom. They're small. They're smaller than Honolulu, considerably, but there are lots of these things. So we have close-up images of a few of them. The one on the left could well be a fragment of a Kuiper Belt object. We've been to Saturn. This is a satellite of Saturn called an irregular satellite with the name of Phoebe. This body also might be an irregular, a Kuiper Belt object that was cast out of the Kuiper Belt at about 3.8 billion years and then captured by Saturn soon after that. Or maybe not. Maybe it formed somewhere else. We don't know. But we're thinking about possible ideas for the way in which these things came to be. This is bigger. It's a 100-kilometer bar right there. It's about 200 kilometers across, so kind of Big Island size. And then here are some of the larger Kuiper Belt objects that have been found. So Pluto is the most famous one and the first one, but these other guys, this is about the same size. These things are strange shapes and similar objects compared to the Earth. They're small, but compared to Pluto, they're significant bodies. So we see a lot of interesting stuff in the solar system that was completely unknown even a decade ago. Now, the last part, I will just go to a slightly different subject. This one is the origin of the Earth's oceans. So this is a project I did with Henry Shea, who was a graduate student at the Institute for Astronomy, now is in Belfast. And I have a movie to begin this that shows what I call the moment of discovery. And so if you thought the first observing movie was fantastic, I think you'll like this one. It's even more incredible. So this is a picture in the Keck control room again. These various computers are hooked up to the 10-meter world's biggest telescope on the top of the mountain. You'll notice this is early in the morning. It's about 5:35 in the morning. We're waiting for the sun to come up in about half an hour, so it's the end of the night. And we're just about to make a fantastic discovery, which is a discovery of the third comet reservoir called the Main Belt Comet Reservoir. So I'll just wait for that and point out when it happens. Okay, it's coming up just about now. Okay, and there it was, right there. Pretty spectacular, huh? So it fits the theme that astronomy is not, astronomers are not very good to look at, but what they do is kind of fantastic, if you don't mind me saying so. I'm biased, but I really think that's true. Here's the issue with the oceans. The question is, where did the Earth get its water? The belief is that the Earth, and there's strong evidence that the Earth was hot when it formed, and probably so hot that it couldn't trap water as ice or as a liquid. It would have been gasified. It would have been a gas, vapor. So people have talked in terms of the accretion of water after the Earth formed. So the Earth took maybe 50 or 100 million years to cool down to even slightly friendly temperatures, and the water and other volatiles were delivered later on, probably by the impacts of some bodies. Maybe, comets are a good source. Comets are full of water. Maybe they dump water on the Earth. Maybe it's some asteroids. We don't know. So people have thought about that for a long time. It's still completely controversial. We don't know where the oceans come from. They probably come from a range of different places. But one place people identified a long time ago was the outer parts of the asteroid belt. People said, we have evidence from the meteorites that some rocks in the outer asteroid belt were once wet. They're not wet now, but they were once wet. And then they were heated up, and the water chemically reacted away. So Henry Shea, for his thesis, started to target objects in the outer parts of the asteroid belt. So the asteroid belt is roughly from 2 AUs. Just now we were talking about 30, and for the Oort cloud we're talking about 100,000, so this is really close. About 2 AUs to about 3.5 AUs from the sun. And we have this picture, which shows this body with this long and horrible name here. It has a nucleus, and it has this long tail of dust that, in fact, goes right across the picture. The arrows were not there when we took the picture. We added them later. But you can see this long tail. These things are stars and galaxies in the background that look like sausages because we've taken many short exposures and shifted them and added them together to follow the motion of this thing. So what is this? This is an asteroid. It's a rock, so we thought. And asteroids should not behave like comets. Asteroids should be just rocks. They shouldn't emit gas. They shouldn't emit dust. So we've continued to look, and we found other examples. Here are a couple more. This is the same one, El Pizarro. This is Reed, and this is 118401 with this little fuzz coming out of it. So there are asteroids in the main belt. By their orbits, they're absolutely indistinguishable from other asteroids. Here, the yellow things are regular asteroids. The red ones are these strange cometary asteroids called the main belt comets. And here's the same kind of diagram, distance from the sun and orbital eccentricity. The black smudge is 100,000 asteroids. The blue dots are 100 known comets. And the red things are these objects at about 3 AU in the outer part of the asteroid belt, all of which look like comets, even though their orbits are the orbits of asteroids. So what we think is going on, I'll skip over that one, is that these bodies, in fact, are comets. They're ice-containing objects that probably formed where we see them now, in the outer parts of the asteroid belt. At very low temperatures, the ice has been trapped since the beginning of the solar system, and then these bodies are activated probably because of a collision that uncovers the buried ice, and then the ice sublimates for a little while and makes a tail and a coma, and we say, aha, it's an asteroid, it's also a comet. So the significance is that these bodies are at exactly the right place, we think, on dynamical grounds and some isotopic grounds to contribute volatiles to the terrestrial planets. So maybe what we've done is discover part of the origin of the oceans. I don't think the oceans come all from the outer asteroid belt. Probably the oceans are a mixture of regular comets from the Kuiper Belt, from elsewhere in the accretion disk surrounding the sun. Maybe some water was brought in on the surface of dust grains, but some contribution is likely from this population that we discovered only 3 years ago, using, again, the smallest telescope on Mauna Kea, the UH telescope. So next time you go down to the beach and see the ocean, which you can do anytime you want in Hawaii, keep that in mind, that you may be looking at the melted main belt comets. So, the message, that's the end of my talk. The message about this is that don't think of the solar system the way it was presented to me when I was a kid. Oh, here are these planets, there's nothing else, and nothing's ever going to change. It's totally different from that. It's much more interesting. A lot of the information in the solar system is carried by bodies that have almost no mass. These are tiny things. The comets are just pathetic little things floating around in the solar system. No mass compared to the planets. But they contain a huge amount of information, in part because there are so many of them, and we can get that information by finding them and by studying their orbits. So that's what Mauna Kea is good for. Thank you.